está mal. Risa. Risa. Que usen.
Dice que no funciona muy bien.
Hola.
La prenda.
Si es más fácil para ellos usar esto, para mí es más fácil que estar con esto.
Yeah. No. If you
So which one would you like to have?
I mean, it has to be.
Like
green.
here, has to be green.
You can have you can toss it around.
Okay.
Like maybe like.
Yeah. It's still on. You can check. There's that function. So it's here. Yeah. I'm really nervous. I'm gonna. Thank you guys all for being here. We are the NSF-IRES project. We have students from 3 different universities. That's the University of South Florida, West Virginia University, and California State University, Chico. And this is an analysis of on-site wastewater systems and interdisciplinary approach. So Luisa kind of went into it already, but so this was a 6-week program with students from those 3 universities, and they were engineering and anthropology students. And we focused on wastewater treatment in the Monteverde zone for businesses. And so for engineering, we looked at water quality analysis and sustainable assessment of these systems. And we also looked at community perceptions through interviews, pulse sorting, and then also surveys of visitors. And this information can be used to recommend recommendations to the community on wastewater management. So the faculty we have that is a part of our project, so we'll get... So we have Luisa here. This is just the power. Hold the cup here. Below it's a piece of paper. Yeah. Oi, oi. Is it still out? Oh, the power's back. Oh, it's still gone? Ay, ay, ay. No, no, no. Yeah, there you go. with a focus on on-site wastewater treatment in Wastewater and businesses. And we did this through engineering with water quality analysis and sustainability assessment, and through anthropology through surveys, interviews, and cross-screening with the community. And we can use this data to advise locals on wastewater management and help with environmental protection and public health. Here are the faculty we want to highlight. So who's our project coordinator here at the Monterey Institute. We have Dr. Naradaza, a principal investigator for PI from the University of South Florida. Dr. Henry, PI from the University of South Florida. Dr. Kevin Warner, a PI from West Virginia University, and Dr. Emmanuel, PI from California State University. Here's our research team. It includes myself. I'm Lauren Berry, an environmental engineering student from West Virginia University.
And me, G. Dago. I'm an environmental engineering student from West Virginia University.
I'm Richard Bajaj. I'm a civil engineering student from California State University, Chico.
I'm Lucas Dahl. I'm also a civil engineering student from California State University, Chico.
I'm Gabriella Brunk. I'm an anthropology student from the University of South Florida.
I'm Natalie Berkazar. I'm the biomedical anthropology student from the University of South Florida.
So before we get into our project specifics, I just want to give you a little bit of background. So we have aerobic treatment, which is wastewater treatment with the presence of oxygen. And so whenever in aerobic treatment, microorganisms, when there's oxygen present, break down organic matter, and this is shown through data like chemical oxygen demand, biological oxygen demand, and total suspended solids. And it also breaks down nutrients like phosphorus and nitrogen. So there are a lot of important biological processes within aerobic treatment. The main one is nitrification, which is a breakdown of nitrogen in the system. The benefits of an aerobic system are that it is more efficient, so it treats those nutrients, organic matter much more, and it can handle a higher flow. Some drawbacks are that it has high operation maintenance costs, so high energy and sludge costs. So wastewater treatment, municipal wastewater treatment, is broken down specifically into black water and gray water. Black water is anything containing human waste. So that includes anything from toilets and urinals. Gray water is everything else. So showers, baths, sinks, and washing machines. There's 3 different scales of wastewater treatment. You have the largest, which is centralized treatment, shown here. And this is in urban to suburban areas, and it's connected through pipes and valves. The next largest is decentralized wastewater treatment, which is here and here. And it is a smaller cluster of systems, and this can be in suburban to more rural areas. And the lastly, is on-site wastewater treatment shown here, which is directly attached to these systems, and it's things like septic tanks. So within the Monteverde zone, we have on that. So it's the Monteverde zone is a semi-rural Vermont region. It has 6,500 residents and 250 visitors annually. So it's very dependent on the tourism industry. All residents use on-site wastewater treatment systems. And gray water is typically discharged to gardens and soil or post-treatment. The gray water is discharged into streets and streets. So an overview of the sampling locations that we chose. All sites can be centralized systems in the Monteverde zone that treated both gray and black water. So site A was the largest, so there were 20 to 40 cubic meters a day. It was an aerobic treatment system and effluent used for irrigation. Site B was 16 to 18 cubic meters a day, aerobic treatment system, and effluent used for irrigation. And site C was the smallest, with 6 to 7 cubic meters a day, anaerobic treatment system, and the effluent is discharged. All site location and details are kept anonymous to maintain confidentiality of these systems.
Hello everyone. I hope the empanadas are good. But my name is Natalie. I'm a biomedical anthropology student from the University of South Florida on the team, and my colleague over here, Gabby, is the other anthropologist. And our objective was to assess the perspectives of diverse stakeholders Okay. Hello. Okay. Ahora sí. But okay. No worries. I can tell you guys what anthropology is all about. Anthropology is the study of people. It looks at the physical, biological, and cultural differences. It helps us understand how people behave, interact with one another, and also interact with their environment. This is important because a wastewater system doesn't just have to work well, it also has to work for the people who use it. And in order to understand the community better, we use 3 different types of research methods. We use surveys, pile sorting, and pile sorting and free listing, and also expert interviews. The first thing that we did was conduct surveys. And we collected 31 surveys on short-term visitors. And the purpose of this was to learn what visitors know and think about wastewater management in Monterrey. Next, we asked locals a very important question. If you own a hotel or restaurant, what would you think about when designing and installing a wastewater treatment system? And at first, that seems like a very hard question. However, this is part of a method called free listing and pile sorting, and I'll walk you guys through it. So we collected 22 of these free listing and pile sortings in Monteverde. And the method sort of goes like this. First, we asked participants to write down their ideas on separate sheets of paper. Next, then we asked them to group those ideas where they make sense to them. And then finally, we asked them to rank groups and explain why they organized it that way. This not really. My voice. Mi voz se fue. Ahora sí otra vez. Pero, okay. This helps us not only understand what people think, what is important to them, but also the amount of knowledge they have on wastewater management. Finally, Finally, we interviewed 3 local experts at each of the sites. We asked them to evaluate their system based on 4 different metrics: social, environmental, economic, and also technical. Their answers not only helped us understand the strengths and challenges of their systems, but also helped us support our sustainability assessments. Thank you. But I'll pass it on to my colleague over here.
So for the results,
and analysis of our anthropological data, we collected demographic data from our participants, including country of residence.
So the demographic data that we collected from our survey participants
reveals that they are pretty evenly split in terms of their country of residence, with 35.5% of participants listing the U.S. as their country of residence, followed by 19.4% listing Germany as their country of residence, with pretty evenly split among.
I'll start over. The demographic data that we collected from our survey participants revealed that they were pretty evenly split across a number of countries of residence, with 35.5% of participants, the vast majority, listing the US as their country of residence, followed by 19.4% listing Germany, with the remainder being from the following countries that you see there on the graph. Participants were also evenly split among age ranges, with the majority of participants reporting their age at
18 to 29 years old, 48.4%.
Followed by 29% who reported being
Age 45 to 59.
33% of respondents reported that they had noticed standing or flowing gray water in the Monteverde zone during their visit. However, most of these sightings were reported as either rare or occasional. When asked how seeing gray water in public would affect their perception of the community, 19.4% of respondents said negatively, 64.5% said somewhat negatively, and 16.1% neither negatively nor positively. Some quotes from participants that help contextualize these results are here on the left, such as the very negative respondent who said that standing or flowing gray water is unsafe and could breed insects or diseases, or our somewhat negative respondent who cited improper handling of water and found it hypocritical. And also, we have a neither positively nor negatively respondent who simply said they try not to assume. All participants reported having concerns associated with wastewater discharge in public spaces. Out of these, 25 participants listed public health concerns, 19 mentioned bad odors, 25 mentioned environmental contamination, 18 mentioned poor infrastructure, 13 mentioned visual aesthetics, and 17 mentioned pests. When asked how concerned they were about wastewater management while traveling, the majority, 32.3% of respondents, reported feeling neutral, with many of them citing that they had simply not considered that when factoring into their travel plans. Interestingly, most respondents who responded somewhat concerned said that they had no explanation for their response. When asked how willing they would be to eat at a restaurant if they noticed gray water on the premises, a majority of respondents reported being very unlikely at 54.8%, or somewhat unlikely at 22.6%. Many of these respondents cited sanitation or health concerns, as you can see in the quote to the left, while many somewhat unlikely respondents said their final decision would depend on additional factors, such as smell or visuals. Finally, when asked how willing they would be to pay a small service surcharge to support water sustainability efforts in Costa Rica, the majority of participants reported being either somewhat willing at 51.6% or very willing at 38.7%. However, as a caveat, many respondents added that they have concerns about transparency or mismanagement of funds or about the surcharge amount itself. Others viewed it as an opportunity to offset the negative impact that tourism can have on the community. Next, we had our free listing and pile sorting results. So we had 95 total cards that were produced across the 22 free listing and pile sorting sessions that we conducted, 85 of which were unique responses. So these were then sorted into generalized labels by theme, as seen in the bubbles over there on the chart. And the most frequently mentioned themes were location, which 8 times, flow rate and land requirements were both mentioned 7 times, and environmental factors was mentioned 6 times. These generalized labels were grouped into overarching analysis categories, which you can see there on the graph legend. And the generalized labels were used to evaluate data in a weighted rank sorting matrix, while the overarching categories were used in a frequency analysis. So for the weighted rank sorting matrix, each participant's cards were given a point value 1 through 5 based on how highly they ranked that item within their piles. And then the point values for all cards were added into a weighting matrix to generate a priority score for each generalized category. So the highest scoring categories, as you can see there on the chart, are land requirements with a score of 38, location with a score of 35, flow rate with a score of 26, and design with a score of 25. One limitation of these results is that certain participants were excluded from the rank sorting matrix for either not having enough cards in their piles or for not having ranked the items within them. And then our frequency analysis revealed that design-related items were the most frequently mentioned, representing 17.71% of all card items, followed by environmental-related items and location and space-related items, which each represented 15.63% of all card items. And then finally, for our interviews, each participant was asked to evaluate their system according to 4 categories, as you can see there: economic, environmental, social, and technical factors, and each of these factors also had sustainability indicators listed below them on the chart. So, as you can see on this next table, there was no single category that was ranked the same across all 3 interviews, with economic factors being ranked the least similarly by the 3 participants. Participant A declined to assign percentages to their piles, their categories. So we asked participants to assign percentages according to what importance they attribute to these factors. Participant A declined to assign percentages, while participant C specifically stated that they believe their percentages reflect how resources should be allocated for the system. So one interesting finding for participant A is that within the social factors category, which they ranked second overall in importance, they ranked community engagement and maintenance as equally important sustainability indicators. They stated, quote, community involvement is important so that they know about maintenance, so that if they ever have a project, they have knowledge of both its structure and its technologies. They also stated, quote, if you explain the environmental aspects to the community, but don't explain maintenance, then it's not a complete picture. Participant B ranked environmental factors as most important overall, and they ranked resource recovery potential as the most important sustainability factor within that category. This is contextualized by several statements that they made about reusing treated water for irrigation, such as in this quote where they said, quote, it's like having a second chance to the water we throw away, and I find that very interesting. Perhaps it's a great help to the environment, since it can be used to water plants, gardens, since it's water that contains natural fertilizer. It's something very beautiful. They also stated, quote, the water contains nutrients from plants and soil, so it's like giving back a little of what we take from the environment. Finally, participant C ranked economic factors as the least important overall, which is reflected in this statement, quote, we're willing to invest whatever it takes to improve. We do it with all the pleasure in the world, as long as we know we're doing things right. They ranked environmental factors as the most important overall, and they ranked eutrophication potential as the most important sustainability indicator within that category. So when explaining the environmentalist mindset found throughout much of the Monteverde zone, they stated, quote, I think that since tourism began, we started to see that a mountain generated more revenue than a farm. And following along that thought process, when they were explaining the importance of environmental factors in their business and their personal life, they stated, quote, we want to instill this in our company culture to make protecting water our way of life.
Can you hear me? Awesome. All right, so the next thing we considered was water quality. We assessed the water quality of each of our systems, and we did that two ways, in-field sampling and laboratory analysis. In our in-field sampling, we collected influent and effluent samples from 5 sampling dates from 3 of our different sites, and that's just the water that goes into the system and the water that goes out. We also used a probe to take the pH, dissolved oxygen, and temperature readings, which can provide important context to our laboratory data. For our laboratory data, we used test kits to analyze chemical oxygen demand, total nitrogen, and total phosphorus, all of which can be used to assess overall water quality and the impact this water has on surface water.
And for our results and analysis for water quality, our first in-field data that we tested for was temperature. Temperature is an important parameter because it can provide some context for observable changes in dissolved oxygen and conductivity within a wastewater sample. In Costa Rica, the allowable wastewater temperature for each system is between 15 and 40 degrees Celsius. As you can see on the graph here, all of these temperatures at each system fall within this range, which is represented by that red line. The average temperature was 25.4 degrees Celsius for site B, which is a degree higher than the 2 other sites in this study. So for pH, the allowable range in Costa Rica is between 6 and 9 for wastewater effluent. The decrease in pH is expected in aerobic systems through the nitrification process, as in sites A and B. This is also why site C you see little change because it is an anaerobic system. The recommended pH range additionally is between 6.5 and 7.5 for discharge to irrigation. This is due to optimal nutrient availability when discharged to the soil. Additionally, we tested for dissolved oxygen. So dissolved oxygen is a very important parameter in wastewater management in that proper levels of dissolved oxygen promote aerobic bacteria function. Adequate DO is necessary for the health of aquatic life. This is above 2 milligrams per liter. And additionally, high or good dissolved oxygen levels prevent bad odors from occurring in these systems. There are no specific wastewater effluent standards for dissolved oxygen in Costa Rica, however. And in Site A, you can see it is a degree higher than Sites B and Site C. It's with an effluent concentration of dissolved oxygen about 3.7 milligrams per liter. Aerobic systems tend to have higher dissolved oxygen contents. So Site A, you can see that holds true, but for Site B, which is another aerobic system, it is a degree lower, which is an outlier in this case. And for Site C, it is an anaerobic system, so this is to be expected. That's a bit lower. Moving into our laboratory data, the first parameter we tested for was chemical oxygen demand, or COD. This is a measure of the dissolved oxygen required to break down chemical organic materials in a wastewater sample. High levels of COD can indicate high dissolved oxygen depletion potential. This is commonly used to assess environmental risk with wastewater. The maximum allowable level for COD in Costa Rica is 150 milligrams per liter. This is represented by that red line on the graph. A decrease in COD across influent to effluent of the system is considered a positive change, with higher percent reductions equaling a more efficient system. So if we look at Site A, a percent reduction of 61.6%, which is a lot higher, a lot more efficient than Site B and Site C, whereas they all do show a decrease overall. Low DO levels in Site B and Site C can be contributed to the fact that they are above this compliance standard. If you look at the darker blue bar at 440 and 317 milligrams per liter, whereas Site A is within that standard. Additionally, we tested for total nitrogen, which is a measure of multiple forms of nitrogen in a wastewater sample. This includes ammonia, ammonium, nitrates, and nitrites. Higher total nitrogen levels can mean an excess in nutrients and a high eutrophication potential, and what that is a high potential for a decrease in dissolved oxygen and high potential for algal blooms in a water source. A decrease in total nitrogen again represents a positive change with a higher percent reduction, meaning a more efficient system. The maximum allowable total nitrogen level in Costa Rica is 40 milligrams per liter. This is not an enforced standard, however, like COD is. This is more of a recommended standard, with a lot of the places that we studied in this research not actually testing for total nitrogen. Site A is seen to be within compliance below that red bar for the effluent at 27 milligrams per liter, whereas both Sites B and Site C are above this standard. And aerobic systems tend to have a more efficient nutrient removal for total nitrogen, and you can see that with Site A with a 33.8%. However, Site B shows an increase from influent to effluent, which is a bit irregular for aerobic systems. And this can be contributed to microbial decay due to the fact that there are low DO levels in the system, not enough oxygen available for that. And finally, for our laboratory data, we also tested for total phosphorus. This is a sum of multiple forms of dissolved phosphorus present in the system, much like total nitrogen, but this includes organic phosphorus and phosphates. High total phosphorus levels, again, can contribute to high eutrophication potential when discharged to water systems into the ground, and it also can affect the DO levels, lower DO levels, and algal blooms can be possible with higher total phosphorus levels. The maximum allowable limit for total phosphorus is 10 milligrams per liter for Costa Rica. Much like total nitrogen, however, this is not an enforced standard, with the sites that we looked at in this study not actually testing for total phosphorus either. A decrease in total phosphorus represents a positive change, with a higher percent reduction, meaning a more efficient system overall. Site A is within this compliance standard of 8 milligrams per liter, whereas Site B and Site C, the effluents do fall above that 10 milligrams per liter guideline at 15 and 20 milligrams per liter respectively. For aerobic systems, you tend to see a more efficient nutrient removal, and in this case, both of these aerobic systems do show this data with a 21.6% decrease and a 25.2% decrease, whereas Site C is not an aerobic system, so it does not follow this general trend.
The next data the study looked at was a sustainability assessment. And the goal of this was to assess the overall sustainability of each of these systems with 3 measures: social sustainability, economic sustainability, and environmental sustainability. The first step to this was the life cycle assessment, comprising of the life cycle inventory, life cycle impact assessment, and life cycle cost analysis. The goal of this was to identify the treatment technology that provides the greatest environmental sustainability while maintaining its effectiveness. We took our data from the LCA, life cycle assessment, and combined it into the C sustainability matrix, which uses engineering, economic, environmental, and anthropological data to calculate a sustainability score. And here are some of the metrics that we looked at. There's 12 in total. the way this tool works is it calculates each raw metric, normalizes it from 0 to 1, and using the equation on the slide there, it develops a score, and the lower the C score, the overall better sustainability. So first, we look at environmental metrics, and you can see here that Site A performed the best with the lowest overall score, and Site C performed the worst. You can see that most of the environmental weight in Site C was biogenic methane, which is to be expected from an anaerobic system because that's a very common output. And here, looking at economic metrics, we can see that Site C performed the best. This is mainly due to the lack of operation and maintenance costs and replacement costs. And you can see that Site B performed the worst due to large capital costs, large labor costs, and not insignificant operation and maintenance costs. And here, looking at our social metrics, you can see that Site A performed the best, even though it had the highest degree of automation. And you can see that Site C and Site B both performed poorly due to their lack of resilience and system intrusiveness.
I just want to say these graphs are really nice that the C2 gives us, and I love these graphs. And the graphs that my colleague showed previously, and the difference between this graph and those graphs are that all the metrics that were shown previously, they are combined into this graph, and they are grouped together. Each metric contribution can be seen as one section across all three sites. And as you can see, Site A performs the best. And this graph, even more like categorizes those metrics into three main sustainability pillars, which is social, environmental, and economic. And all these metrics are given even weighting. And according to this graph, Site A performs the best because it has the lowest score, which means that it was overall more sustainable. We can see that Site B had the most impact, had the highest score, which means it was the least sustainable, and Site C performed well economically, but the environmental and social categories higher its score. Now, the difference between this graph and the previous graph was that the C tool has a feature which allows us to change the weighting of these three pillars. And in this graph, the economic category is given more weight. And as you can see, when the economic category is given more weight, Site C is the preferred alternative as it has zero maintenance cost and no operation and maintenance. Similarly, in this graph, the environmental category is given more preference, and Site A again performs the best throughout all the sites. And the key takeaway from this graph is that you can see in Site C that even though the economic costs are pretty low, the environmental impact is so high that it turns out to be overall higher than Site A. So this is something that Site C can take away from it and work on its system. Now in this graph, finally the social factor was given preference, and as you guys can see, Site A performed well again, whereas Site B had the highest score, which means it had the least sustainable system across all three systems. And if Site B wants to improve their system, they can work on their social metrics and try to get the score down. One thing I want to remind everybody is that the graphs that the C tool gives is not to give us a perfect understanding or a perfect wastewater system. It is for us to get a holistic or an overall better understanding across all three categories.
All right, now our recommendations and conclusions. So before I get into that, just a couple of key takeaways from our results. So our survey data found that the visitors had a negative perception of gray water, and it may deter tourists from specific businesses if there's gray water on the premises. In free listing and file sorting, the most listed were land requirements, location, flow rate, and environment. Highest weighted was land requirements, location, flow rate. In the interviews, the environmental factors performed well in all interview participants, however, with specifically 2 interview participants rated the highest overall. In our water quality data, Site A consistently performed the best, with Site B and C consistently out of compliance, specifically with COD, total nitrogen, and total phosphorus. In our sustainability assessment, Site A performed the best in 2 out of 3 metric categories, with only not performing the best in the economic category. So overall recommendations and conclusions, we gave each specific site a detailed report of our recommendations to those sites, and our overall site recommendations are that they improve operations and maintenance and monitoring, and then also help with address performance issues within each system. So we recommend that decentralized aerobic cluster systems are suitable for small communities in Monteverde. The flow rate of the most sustainable system, Site A, was 40 cubic meters per day, and that's equivalent to about 30-40 households within Costa Rica. This would treat both gray and black water, so it would reduce the amount of gray water in the streets, improve public health and environmental and visitor perception of the environment, and also have a smaller land footprint than on-site septic systems, which was very important with locals' perceptions. This is a view of a community within the Monteverde zone, and this, if you use the numbers of 30 to 50 households, we could add 2 cluster systems within this, reducing the land space and improving the environment. We have a couple of thank yous. So thank you to our research participants, Andrea Solano, Dr. Eric Centeno Mora, Dr. Alan Feldman, Devin Gray, and all of the project guys. As a thank you to Gabriella Wong and all of the NVI staff, our host families and people back home, and special thank you to our queen, Luisa Moreno, which without her help, this wouldn't have been possible. So the material is based upon work supported by the U.S. National Science Foundation under grant number 2246348. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation. Do you have any questions?
Where there is like no space.
Yeah. So decentralized systems kind of like as it supports a cluster system. So any land requirement would be much lower, and so there still would be necessary piping done because of course there's no space in that community. However, it would still be more beneficial and it would treat the overall health of the environmental impacts and reduce land requirements. Did I address your question? Do you want to?
So we recommend a system similar to the system used in Site A because we found that that was the most sustainable, and we found that it would be easily applied to a cluster of houses and homes, which can then handle that flow rate and take up less space than your current septic systems, and also handle gray water as well. Does that answer your question?
I guess I just missed exactly which system was A and which was C. So maybe just quickly.
So this is the detail of all of our sites, and you can see Site A handles 20 to 40 meters of wastewater per day.
I remember that, but what exactly was Site A? Like what it looked like?
We can't show you the specifics to maintain confidentiality for each system, but it's an aerobic treatment system, which means it uses an aerator to do most of the work, and it has a very small footprint. But that's all we can tell you.
Is it like an open pond? Or
no, it's closed. It's like tanks, but again, that's all we can say. Anyone else?
That's a good question. Because I mean, like what I came to learn about, what we can actually do. And if I don't know what it is, then I'm going away with a lot of really good information and with a lot of pictures. And just missing that one part.
Actually, we would love to talk to you more, but there's limits to what we can say to make it confidential.
We can make it generic, like a generic picture of what that would look like.
Thank you guys for your support. Student in the back. Yeah. Gracias por venir.
Specifics, but we can come up with like a generic. I get it. Yeah, it's good work. Thank you so much. Thank you.
almuercito. Entonces podemos ir saliendo y ahorita ya nos lo sirven. Y tal vez hacemos una pequeña actividad después del postre. Con gusto.
Are there still 20 people in here? Oh, what's? I want to see how many. I want to see what the chat has to say.